Alright class, let's go ahead and solve a problem based on the combined vapor power cycle. So in this problem, problem number 1077 from the textbook. Okay, so in this problem it's telling us that it's a combined gas and a vapor power cycle. So you can see this problem is telling us that the gas turbine portion of a combined gas steam power plant has a pressure ratio of 16. So that means that it's a combination of the gas and steam power plant, combination of gas of steam power plant, right? It's a combined cycle. And then it has the pressure ratio, and it has given all those information. Before going to the take a look at all those information, let's take a look on the TS diagram first, how it look like for this particular combined cycle. So basically let's start with the gas power cycle, the top one, right? So in the top one we can see that from 5 to 6 it's a compressor, temperature and pressure is increasing. So this would be 5 and this would be 6, and then 6 to 7 it's basically here this Q addition, or the heat in constant pressure heat addition is happening, right? So it will be like right here. So 6 to 7, and then from 7 to 8 it's passing through gas turbine where the pressure is dropping and as well as the temperature is dropping, right? The temperature is dropping. So this would be like this. So the 7 and 8, and from then 8 to 9 heat exchanger is coming. So it will be 8 to 9, right? Now and then from again it's coming to again it's 9 to 5 it's coming basically to the the compressor. So this is the gas power cycle, right? What is happening in the vapor power cycle or the steam cycle? So basically in this one we can see that from 1 to 2 the pump basically it's increasing the pressures and slightly increasing the temperature as well. So it would be 1 to 2 1 2, and then from there it's going to be like this. So this is 2, and then constant pressure heat addition, which is 2 to 3, and then 2 to 3 is heat addition in the heat exchanger, and then 3 to 4 is the turbine. 3 to 4 is the turbine right here, and then 4 to 1 is the condenser. So now we know that basically all of the TS diagram, and we know that Q in is happening in this one, combustion chamber 6 to 7, and Q out is happening right here, condenser, from 4 to 1. So now let's take a look what are the informations is given for this particular problem. So first of all, the pressure ratio is given for this one. So that means P6 divided by P5, it's given 16. Air enter at the compressor 300 Kelvin at a rate of 14 kg per second. So this means we have given the T5, which is 300 Kelvin, and then we also have the mass flow, and then heated at 1500 degrees C in the combustion chamber. So the T7 would be 1500 degree C, right? And then this is the maximum temperature of this cycle, and then combustion gas leaving the gas turbine and used to heat the steam, which is 400 degrees Celsius. Okay, 400 degrees Celsius. So this 400 degrees Celsius and then at 10 megapascal in the heat exchanger. Though the combustion gas leaves the heat exchanger at 420 Kelvin. So the combustion gases leaves the heat exchanger at 420 Kelvin, and then right here, right, 420 Kelvin, and then they're telling us that the steam leaving the turbine is condensed at 15 kilopascal, right? So basically right here, so leaving this line is 15 kilopascal. So this is 15 kPa, this is 10 MPa megapascal, and we do have, this is 1500 degrees Celsius, this is 400 degrees Celsius, right? And then what else we got? Inlet temperature was 300 degree Kelvin, right? Actually this is Kelvin, excuse me. This is Kelvin, all of them are Kelvin, okay? So it will be Kelvin. Okay, all right. So now they're asking us that what is the mass flow rate of the steam, right? Number one, and number two is the net power output of this cycle and the thermal efficiency of this combined power cycle. So we'll analyze this cycle one by one. So first we'll analyze the top portion, which is the gas power cycle, right? So gas power cycle is nothing but 5, 6, 7, 8 and 9, right? So let's take a look at a gas power cycle. So assumptions for these problems are: number one, air standard assumption. And then steady state operating condition. And then number three is kinetic energy and potential energy change is negligible. Okay, now and also, since a gas power cycle, we will use the air properties, right? Air properties is basically the Cp of air, it's 1.005 kilojoule per kg Kelvin air, right? And K equals to 1.4. all of them came from table A2. Okay, so now analysis or solution, right? So let's take a look at the cycle right here, 5 to 6 and 6 to 7 and 7 to 8, right? What is happening? So if we take a look at process 5 to 6 process 5 to 6, it's a ideal and isentropic, right? Ideal gas and isentropic condition, isentropic compression, actually compression. So then the formula would be T6 divided by T5 equals to P6 divided by P5 to the power K minus 1 divided by K, right? What are the things we know here? So we don't know about the T6, however we know the T5, right? And we also know the pressure ratio. So the pressure ratio, which is nothing but the pressure after compression divided by pressure before compression, so which is 16, it's given for this particular problem. Okay, so it will be 16 to the power K, which is 1.4 minus 1 divided by 1.4. And then T5, we also know that the T5 is inlet temperature, which is 300 Kelvin, right? So let me plug it, 300 times 16 to the power 0.4 divided by 1.4. okay, so if we solve this, it will be T6 equals to 662.5 Kelvin. Okay, so we know the temperature of at point 6, right? So now from 6 to 7, what is happening? Process 6 to 7, constant pressure heat addition, constant pressure heat addition, right, in the combustion chamber. So basically we know that the Q in equals to mass flow of the air times H7 minus H6. okay, so instead of enthalpy, if we use the temperature, then it will be mass flow of air times the T6, air times Cp times constant pressure specific heat, and then T7 minus T7 minus T6. Okay, so we know everything here. Mass flow was given like 14 kg per second, and Cp, which is 1.005, right, times the T7 maximum temperature of this cycle is 1500 minus T6, we just determined 662.5. so if we now the Q in equals to would be 11,784 kilowatt. Okay, that's a large amount of heat generating in the combustion chamber. Okay, so now in the process, basically in the process 6 to 7, which is the WC or work consumption, right, work consumption in compressor. What is that? WC equals to mass of air times H6 minus H5. So mass of air times Cp times T6 minus T5. So we know all of this information, which is 1.005 times T6, we just got it 662.5, and inlet temperature was 300 Kelvin. So the WC, so the WC would be 51,000 kilowatt, right? We have Q in, W in, right, both of them. Now let's take a look at the process 7 to 8. For process 7 to 8, right, so for process 7 to 8, constant pressure, isentropic expansion in the turbine. What is happening here? So the formula is, we know that T8 divided by T7 equals to P8 divided by P7 to the power K minus 1 divided by K, right? So basically in the pressure ratio, which is constant pressure, so the if we look at the PV diagram, if we can draw the PV diagram, in the PV diagram we'll see that, you know, this basically this T8, which is equals to, it's a constant pressure, right, and then T7, so basically T7 will be equals to T6, and T8 will be equals to T5, right? Oh no, I'm telling wrong thing. So basically the P6 equals to P7, and then P8 equals to P5. Why? It's basically this P6 to P7, it's constant pressure heat addition. Similarly in the you know, in the environment, when it's exiting the turbine, it's becoming the, you know, atmospheric pressure, which is the inlet pressure of the compressor. Atmospheric pressure is P5, which is equals to P8, right? So P8 and P5 is the same. So that means we can write this expression like this, P5 divided by P6 to the power K minus 1 divided by K. Again, T8 equals to T7 times P5 divided by P6 equals to K minus 1 divided by K. And we know that P6 divided by P5 equals to 16. So instead of, so the P5 divided by P6 would be 1 over 16. So T8 equals to, T7 was 1500 maximum temperature, 1500, 1 over 16 to the power. So the T8 would be, if we solve this one, the T8 would be 679.3 Kelvin. So now we know the temperature at 0.8. Okay, so what would be the work output, or W turbine? Mass of air times H7 minus H8, right? So mass of air times Cp times T7 minus T8. We know all of them, okay? Mass is 14, Cp is 1.005 times T7 maximum temperature 1500 and T8 679.3. okay, so if we solve this, W turbine output, right, of that gas power cycle would become 11,547 kilowatt, right? What would be the net work output? So the W net would be W turbine minus W compressor, right? So the W turbine minus compressor 11,547 minus 5100 equals to 6447 kilowatt. So that's our W net, okay, for gas power cycle. Now let's take, we did pretty much everything for the gas power cycle, right? We know that what is the W compressor, we know that what is the W turbine, and we know that what is the Q in, right? Everything about this gas power cycle. Now let's take a look at that steam power cycle, right, or the vapor power cycle and the bottom cycle. What is happening? So if we start from the process 1 in the bottom cycle, right, for the steam cycle, right, if we start from the point 1 or the state 1, state state 1, what are the information we have given? We have, right? So at the state 1, basically we have the pressure equals to 15 kilopascal, right? With respect to this 15 kilopascal pressure from the table A5, we will look at the saturated the saturated point, because it's residing on the saturated line right here. Okay, so now for that one, H1 equals to HF, which is equals to 225.94 kilojoule per kg, okay, and then V1 equals to Vf equals to 0.001014 meter cube per kg, okay. We know this information. Now what is the pump input, right? So we know that W pump input equals to specific volume times P2 minus P1, right? So specific volume is 0.001014 times P2, which is 10 megapascal, which is 10,000 kilopascal minus 15 kilopascal, okay. So W pump in, and W pump it in would be, if we solve this, 10.12 kilojoule per kg, okay. So from here also we know the formula for the W pump in equals to W pump in equals to H2 minus H1. So H2 would be H1 plus W pump. So the H1 we know that 225.94 plus 10.13. So H2 will be 236.06 kilojoule per kg, okay. So we know that point 2. Now let's move on to the state 3, right? At state 3 we have the pressure, which is 10 megapascal, right? 10 megapascal or 10,000 kilopascal, and then we also have the temperature T3, which is equals to 400 degree Celsius, right? So with respect to this 400 degrees Celsius, as well as the is it 400 degrees Celsius or Kelvin? Excuse me. Actually, this is 400 degree Kelvin. Okay. The problem. Let's take a look. No, it's Celsius. .400 degrees Celsius. Okay. So with respect to this T3 equals to 400 degrees Celsius, we from the table A6, right? From table A6, we'll get the H3, which is 3097 kilojoule per kg, and S3 6.2141 kilojoule per kg Kelvin. Okay, so we have this information from state 3. Now at state 4, how do we determine all this information? In state 4, we have the pressure P4 equals to 15 kilopascal, and then we also have entropy S3 equals to S4, because it's a isentropic process, entropy are equal, 6.2141, right, kilojoule per kg Kelvin. We have all this information. Now if we basically in the point 4, if we take a look right here in this diagram, we need to determine the quality of the steam, so X, right? So with respect to this pressure and entropy, we should also record the SF, right? SF, which is equals to 0.7549, SFG, which is equals to 7.2522, okay, and then SF, which is equals to 225.94, and SFG, which is equals to 2372.3 kilojoule per kg Kelvin, kilojoule per kg Kelvin, kilojoule per kg, and kilojoule per kg. Okay, we have all this information. Now the quality of the steam, we know that X formula would be S4 minus SF divided by SFZ. So if we plug in all this information, it will be 0.7528. This would be the steam quality. Okay, so now for this steam respective steam quality, what would be the H4? H4 is nothing but HF plus X times SFG. So we know all this information, right? So if we plug in, it will become 2011.8 kilojoule per kg, right? H4. So now we know at the point 4 as well. So if we do the energy balance, right, then in this key component, which is the heat exchanger, so I'm gonna go ahead right here, this heat exchanger. So let's take a look what is happening in this heat exchanger. Okay, this heat exchanging part, what is happening actually? So this is the heat exchanger. In the heat exchanger, air is coming from turbine number 8, right, and then exhaust is going to the compressor, which is number 9, right, air. So this is M air, right, and this is exhaust gas. exhaust gas. And similarly, mass of steam is coming to this heat exchanger, and that mass of steam is going to the turbine, right? So basically this is the heat exchanger. Okay, so if we do the energy balance of this particular heat exchanger, then what we will see? So if we do the energy balance, then we will see that E in equals to delta E of that system, right, which is equals to 0, because net input and output of this system, of this system are equal, which is 0, right? So basically if we do this, then it will be, E in equals to E out, right? So it would be summation of input enthalpy and then equals to summation of output or exiting enthalpy, right? Exiting enthalpy. So basically the input enthalpy is nothing but the steam, right? So steam is like this, H3 minus H2 and mass air, which is H8 minus H9. Okay, so from here we can determine that mass of steam, right? Because we know everything here. H8 minus H9 divided by H3 minus H2 times mass of air, right? So we know all of this information, right? So ms would be Cp times T8 minus T9 divided by T3 minus T2 times mass of air, mass flow rate of the air. So if we plug in all this information, ms would be 1.005 times T8, we determined 679.3, T9 was 420 Kelvin divided by T3 is equals to 3097.0 minus 236.06. okay, and also the mass flow, which is the 14 kg per second. So the mass flow of the steam, which is equals to 1.275 kg per second. So this is the number 1 answer. Okay, then the number 2 is asking that what is the net output of this system, right? Network output of this system. So number 2, or let's express it in B. Okay, this is A, and the B is basically the net output. So the W turbine of that steam turbine, it's equals to, we know that mass of the steam now, which is H3 minus H4. So it would be mass of steam times Cp, or we already determined the enthalpy. So basically plug in all this information, right? So 1.275 times 3097 minus 2011.5. So it would be 1384 kilowatt. So W turbine of steam. Okay, and then W pump, what would be the W pump of steam? So it would be mass of the steam times W pump. Basically we know that 1.275 times the W pump, which is 10.12, right? It would be kilowatt, so 12.9 kilowatt. So we know that W pump and W turbine for this steam cycle as well. So right? So the W net would be, or W net of the steam would be equals to W turbine minus W pump. Okay, so the W turbine minus pump 1384 minus 12.9, which is equals to 1371 kilowatt. Okay, so this is the steam. So what would be the, actually this is for steam. Okay, steam. What would be the combined power? So the W net of combined cycle is the W net for steam plus W net for gas, right? Gas per cycle. So for the steam we just saw it's 1371 kilowatt, plus for the gas it was 6448. So the W net of the combined cycle would be 7819 kilowatt. Okay, so that's the answer, W net of the combined cycle. And then the efficiency, the last portion, thermal efficiency of this combined cycle. So the W net of this combined cycle divided by Q in, right? So W net of the combined cycle, we just saw it 7819 divided by 11,784. So it would be 66.4%. Now you guys see that the efficiency of the combined cycle is double, right? So usually efficiency for gas power cycle or steam cycle, we saw that it's 20 to 30%. Now it's went up to all the way to the 66%, right? So the combined power has the highest efficiency. Anyway, so that's all about this combined cycle power plant. I hope you guys got it through this TS diagram. And yeah, thanks for watching this video, and we'll come back with the new chapter.